All right, let's get started. Exam tomorrow from 1 to 3:50. In Boardman, I keep forgetting the number, 206 or whatever that number is. It's on that hall. You're allowed one note card. And I will give you a table of block diagram map. I'll give you a little bit more detailed one than the one that you have. So if it's helpful, great. If not, that's okay. Make sure all the other equations you need. There shouldn't be that many. There's not too many, but the rest of them you should be okay. So let's go through the topics and feel free to interrupt as we go, because again, this is just the document that I put together. So giving you some tips about what to focus on. And it's also a high level review, right? That's why it's called the exam 2 review. So we started out with pole zero maps, and we discussed pole zero maps last semester a little bit in 324, if you recall. And we keep coming back to them because we really find that our pole zero maps tell us a lot about the stability of a system, and we can use our S-plane plots to say, let's do some more sophisticated analysis. Let's start to dig into these things a little bit. So it's worthwhile for us to spend more time kind of reviewing it. So we talked about Bible stability, bounded input, bounded output. So if the input is bounded and the output is bounded with that input, then that's considered a Bible stable system. All right, that's an important part. If it's in the left-hand, or I should say if all the roots of the denominator of the characteristic equation, so we got to keep adding that in. You have a characteristic equation, which is the denominator, but you have a transfer function for the overall system. So if all the denominator roots or all the roots of the characteristic equation, that's saying the same thing, are in the left-hand half plane, then you have, by definition, a stable system, because all of the terms will have some e to the minus something t, which decays away. It might take a long time, but you're definitely going to get some decay eventually with respect to time. So your system is going to be Bible stable. If you have any pole, any single pole in the right-hand half plane, then by definition, the system is unstable, because when you go back to the Laplace domain, that e to the positive t blows to infinity as time increases. So your system becomes unstable. And finally, if you have any pole, which means you have to have at least one, and normally you have two, if you have any pole on the j omega axis, then the system is marginally stable. Why is it marginally stable? Because you need to know what the input of the system is to truly determine what the stability is. So if you have an S or a pole at S equals 0, that's by definition, this is an integrator in the time domain, which if you're integrating a sine wave or a cosine wave, no big deal, right? That's still a bounded output system. The problem is if you're integrating a DC input, over time, that DC input is going to go up and eventually peg out, to damage whatever piece of equipment you may have. So that's why you need to do the input, because a sine or a cosine wave, that integrator doesn't care. It'll do it, and then you get a bounded output. But for a step input, it has a problem. The same thing, if you isolate something or excite something at its natural frequency, the concept of a tuning fork, when you tap something and it vibrates at a very specific frequency for a long period of time, that is its natural frequency. So if it has no decay, if you tapped it once and it rung forever, which doesn't really exist, then that would be a system that you could potentially excite that. You could tap it at the same frequency, and eventually that would just continue it would increase its amplitude until it would break your tuning fork. So that's where we came up with the marginally stable system. Now, the only other thing we want to say is, or we have to decide is, what about our poles and zeros? So remember, in the denominator are our poles, and in the numerator are our zeros. And in general, what we said is the number of poles is going to be greater than or equal to the number of zeros. But that's not 100% true, right? Because if we append that a little bit, the number of total poles has to equal the number of total zeros. Why is that? Because the total poles, that's equal to the finite plus the infinite poles for zeros, right? So the total poles, you have to include the finite or the infinite. More importantly, though, normally, if your real poles or your finite poles, you're always going to have equal to or greater than. So it would be better to say that this is the zeros. The total zeros is going to be equal to your finite plus your infinite. And when you do that, you should always have the same. This will make a lot more sense had we had a class before this class, because remember, snow prevented us from having a class last Thursday, but we would have actually developed the concept of root locus, and you would have actually seen that being implemented. So with that being said, we'll just need to make sure we do that. And so that's when you allow this S to approach infinity, and that's where you find your finite poles or finite zeros, infinite zeros. These I can't talk today. Okay. So essentially what we're saying is when you do the limit as S approaches zero, or S approaches infinity, sorry, of the denominator and the numerator, eventually you're going to have an S to the M divided by an S to the N. And in most real world systems, N is going to be equal to greater than M. And so what we see is that this is going to be equal to 1 over S N to the minus M. And when I allow S to approach infinity, what ends up happening is that we end up with 1 over S approaching infinity, which turns into a 0. So this actually becomes the 0, right? So that's where we get the zeros from. That's where you can do the math. Okay, questions on pole zero maps and understand that, because it really leads well into root locus plots quite a bit. And it also helped us when we looked at root Hurwitz, when we saw the concept of when we crossed the J omega axis, we used that auxiliary equation, and we started to see a little bit of information about that. Okay, as I talked about, or I promised last semester, we did all that partial fraction expansion math, and you had to have your fingernails pulled out to do all that stuff to be able to go back into the time domain. We much prefer to live in the Laplace domain to do all our calculations here. So here's the first case where we've got a block diagram of a system, and its system has a first order response, which means that all it has is an S plus A in the denominator. That's our first order system response. I don't know what the numerator is. I don't care. I just know that we have an S plus A is the highest order S term in the denominator. And if we do that, we can use these equations. We can find our time constant by inverting the A, 1 divided by A, because we know that this into the time domain becomes e to the minus a t, but our time domain approach is e to the minus t over tau. So if we do some math, we see that A is equal to 1 over tau. That's how we can solve for our time constant by using that value of A. And once we have the value of A, we can use the rise time calculation, which is an approximation. It's not exact, but it's close enough. We just take 2.2 and we divide it by A, or we just multiply that by our time constant. Either one's the same approach. And that again is the rise time to go from 10% to 90%, not from 0 to 100. And the reason why this was developed however many years ago is it's much more useful for us to know that our system has started timing when we're about 10% of its final value. So you're recording something and you see something bouncing around 0, not really doing much. But when does it actually start to rise up? So once we hit about the 10%, we're assuming that the system has actually started to respond to some sort of stimulus, and now it's going to go up. Same thing for getting past 90%. It essentially takes infinity for the system to reach steady state. So obviously the rise time, if you went from 0 to 100%, would be infinite number of seconds. So let's stop this at a realistic output. Let's call it 90%. So 10 to 90% is 2.2 divided by A. And then if we want to use the 2% settling time, that's just going to be equal to 4 divided by A. All right. These equations only work if they're first order systems. Okay. They don't work for second order systems. Questions on first order systems? Okay, so let's move to a second order system, and a second order system has an S squared plus AS plus B in the denominator. And we recognize that that S squared plus AS plus B is generic because we don't necessarily know how the system is going to respond. So if you remember, when our second order system, we had 3 different cases. We had the case of an underdamped system, an overdamped system, and a critically damped system. Well, that was all well and good, but what we didn't understand is how do we use it? So we redefine these to say plus 2 zeta omega sub ns plus omega sub n squared. And now, squared, sorry, hard to write on the keyboard. And now once we have this information, we're actually able to start to look and say, wow, I have some really interesting components here. My omega sub n is the undamped frequency. My zeta is a damping ratio. And once I have that, now I can go ahead and I can define or specify what the categories are. So let's just do this on another one so I keep, instead of jamming. So I have overdamped, underdamped, and critically damped. And with the type of damping that we have, if it's an overdamped system, then zeta is greater than 1. If it's an underdamped system, then zeta is less than 1, but it always has to be greater than 0. Why can't the system be less than 0 or zeta be less than 0? If we go back to our denominator here, why can't zeta be less than 0? We know omega sub n has to be positive, right? You can't have negative frequency in the real world. So we have to have a positive frequency. So why can't zeta be negative?
We only have S squared plus omega squared.
Plus what?
Omega of the n squared.
Well, if zeta is less than 0, why would that make that number?
Negative.
So you're saying this is going to be S squared minus 2 zeta omega sub ns plus omega sub n squared. What's the problem with that? Why? Is it impossible? Very good. It's an unstable system, right? What was our criteria about Ruth Hurwitz? What's that? All these coefficients have to have the same sign, right? Do they have the same sign? They do not. So any negative coefficient, when the rest are positive, is going to be an unstable system. So how can you have damping if the system blows to infinity? It's inversely damped, right? So you can't have a zeta less than 0 because you wouldn't have any damping at all. The system would actually be growing larger. And a critically damped system, zeta is equal to 1. When we do that, I should have put this in a different spot. Let's see if I can clip this here. Move this around. Let's see. Give me 1 minute. I'm trying to figure out which is the special key that I can. I think it's this one right here. Try that again. Okay, let's see if I can move this. Perfect. Okay, so when I have overdamped, I have two real roots. And they are unequal. If it's underdamped, I have two complex conjugate roots. So just so that we know, they can't be equal because they have to be complex conjugates of each other. You can't have a 3 plus J4 and a 3 minus J4. It's not going to work, right? It has to be a 3 plus J4 and a 3 plus J4 for complex roots. You have to have the plus J4 and the minus J4. And over here, I have two real roots, but they are equal to each other. Okay. And what that means is when I look at the characteristic, here's what my steady state value should be. If it's a overdamped system, you kind of reach steady state at that one. If it is a underdamped system, you have some overshoot. And then it reaches steady state. If it is a critically damped system, you have one that doesn't have any oscillation or ringing, and it reaches steady state very quickly. The reason why we like to use an underdamped system is because if systems degrade over time in the real world, you can get some changes. And so what happens typically is systems get less efficient, meaning less, they have higher damping because you have more resistance. And so a system that you did for critically damping here would actually move to the underdamped system. So the system would take longer to result in reaching steady state. Where if it's an underdamped system, you're allowing some increase in the damping, which is just going to get you closer and closer from here, hopefully into a critically damped system before you have to go back and redo the system entirely. So the critically damped system is ideal, but it's not going to last forever or even that long. So you're better off to switch to the underdamped, work on your system, and go from there. Okay. So the second order system, now we know if it's an underdamped system, okay, these equations are the only ones that are applicable. We can calculate percent overshoot, and the percent overshoot is zeta. And the reason why we calculate zeta this way is because we're trying to limit percent overshoot to a certain value. This one you may want to think about in advance for the test, because if I ask you to calculate zeta given some design parameters, you're going to perhaps struggle to solve that equation for zeta, right? That's not the easiest equation to do algebra on. It's not impossible, but you have to do a little bit of work. And the best case scenario is you can calculate your percent overshoot or your maximum percent overshoot, because that's the only equation that has zeta. If you look at my peak time and my settling time, those both have zeta and omega sub n. So if you're trying to design a system that has a zeta and omega sub n that are adjustable, you'll notice over here, if I pick zeta, then I can calculate omega sub n. Or if I pick omega sub n, then I have to calculate zeta. So you're just kind of going back and forth. Where if you start over here, all I calculate is zeta. No omega sub n calculation. And then once I have that, then I can substitute it in for any of these other equations. So peak time, settling time. Peak time is how long it takes to reach a peak. And this is interesting because remember how we talked about first order systems with rise time, we went from 10 to 90%. That doesn't apply on second order systems. Second order systems is you start at time 0 and you go to the peak time. I believe the reason why peak time was specified that way is because if you remember for a second order system, it ramps up pretty quickly to get that overshoot. Where if it's a first order system, it kind of does one of these, right? It doesn't ramp as quickly. So it's harder to tell when it actually goes up. I guess that's the reasoning I find for it. I don't know. I mean, these equations were determined many years ago, so I'm not sure. And then here's my equation for settling time as shown. You'll also see that I have omega sub d, which is omega sub n times the square root of 1 minus zeta squared. That's just if you have damping in your system. So if this term here does not equal 0, then when you do the quadratic equation, you're going to end up essentially this one. So this is the actual frequency that the system experiences. But the undamped one, omega sub n, it's going to be a different frequency. So interestingly enough, when you add damping to a system, you actually modify the frequency. So it takes longer to reach steady state, right? But you got to do it because the undamped natural frequency just oscillates forever. So it rings at a higher rate. So you get some elongation, if you will. That's why if you look over here, if you look at critically damping, or underdamped system, we can see that if zeta, let's say zeta equals 0.9, we get that characteristic here. But then if we have this, over time, this is zeta equals 0.1. So its oscillatory frequency is much higher, much faster, and it oscillates higher, but you can see that it reaches its peak faster than this one does. And the reason why it reaches its peak faster is because of the oscillation frequency. And hopefully you can see that here. When I plug in 0.1 for zeta in there, it's 1 minus 0.1 squared times omega sub n. That's a lot closer to omega sub n than 1 minus 0.9 squared, right? So you can see that my frequency drops by quite a bit as I increase my zeta. Okay, any questions on second order systems? Okay. Block diagram math. Hopefully pretty straightforward and simple. So block diagram math is just combining blocks and simplifying them down to hopefully end up with just one feed forward path. And when you do that, you can find the characteristic of equation. So all this work that we've been doing is all hinging on being able to get the characteristic equation. But in the real world, most of us, at least I'm not smart enough to be able to look at a system and say, here's the simplified equation of the system. So what I need to do is I need to take one piece at a time and figure out how to model that system. And then I assume that there is enough difference between the two system blocks that I'm modeling so that interstage loading doesn't impact it all that much. So I can model part of this system, next part, and then I can put them all together and have a reasonably accurate system. And so when I do that, I create many of these little blocks here, maybe hundreds of these blocks that I need to combine down into one simplified block so I can solve for the characteristic equation. So this is the process. This is one of the tables to go ahead and calculate that. So the first one, you put blocks in cascade, just multiply them together. If you add or subtract moving forward path, so this is just basically a parallel path, you add or subtract. If you're moving a pickup point from the left to the right, or moving it behind the block, that pickoff point did not multiply by the gain. Once you move it past the block, now that pickup point has been multiplied by the gain, so you get to divide it out to get the same results. If you go in the other direction, move the pickoff point from right to left. In the first case, you can see that I'm actually multiplying it by the gain. In the second case, I'm not. So to make that point equivalent in terms of feedback, I've got to add my gain block into that feedback path to go ahead and do it. And then the last one is moving a summing junction. I guess these are kind of the same, which is you move it to the left or to the right. It's the same deal. You just have to figure out, am I multiplying the gain, or am I moving the block before or after? So if I do it before, then I've added something in that hasn't had that chance to multiply the gain. So I've got to add those two together. If I do it behind, then I've got some problems here where I have to take that gain away. So that's why I have to multiply this one by G over here, because the summing junction over here would only have me multiply U1 times the gain, but I need both of them, so that's why I've got to add it in there. And in the other case, if I move it to the other end, you can see that U1 is multiplied by G1. If I move the block over here, now this U2 is also being multiplied by the gain, so I've got to divide it up. And that's what we're doing over here. So the way to tackle these problems, the best way to tackle these, in my opinion, is just to think about what you're trying to do, you know, and what is happening to the inputs. So sometimes what helps me is I will actually look over here and I'll say, all right, I'm going to look at this block. So let's go ahead and go over here. I have X coming in to G1, G2, and then I go out on Y. So what I'll do is I'll do it individually. I'll say, all right, well, here's my X signal, and I multiply that by G1. Oh, one moment. It's kicked off. What happened? Oh, wait. You just kicked on? I don't know what happened.
Maybe the material was too much.
Yeah, the material is too much. Sorry, folks. Just give us 1 minute where the projector just decided to turn off here. So I'm not sure why it did that. All right, let's try it again. These smart boards are getting old, so I might need to replace them. Guess the smart board time is coming to an end. If we've got a projector here, we just need to take out the smart board and slide that down. Does John use the actual whiteboard to write on, or does he just write on his computer?
Same thing as you. Oh, yeah.
Yeah, we probably should take it out and just rewire it. So that thing is a lot more expensive. All right, we're back. So what I have over here is my inputs, my block. So what I can do is I can see that I have G2 over here. The point over here is XG1, and that's the block, or the input that goes there. So I've just taken out my G1, and my input to G2 is here. And then my last case is XG1, G2 is my Y. They're the same thing. So now if I want to replace this, I can see that X had to be multiplied by G1 and G2. So for equivalency, I just have a single block with my input and my output. So if you're stuck and you're not exactly sure what to do, just try to break it down like this. Same thing with a summer or moving a pickoff point, right? So if you have G1 over here, and I have X going in over here, and I want to go ahead and move that over here, I can see that when I redo this, my block, my output over here, well, let me just do it over here. This is XG1, and this is just X. So if I want to move my pickoff point to this location over here, here's G1. What should be coming out of there is XG1, correct? What's coming out over here is not X, it's XG1. So if I want these to be the same, I divide that by G1, and now I have X, and so it's the same value. See the equivalency? This is XG1, and this is X. If I move my pickoff point to the right-hand side of the block, I have my XG1, so I'm good to go over here. But unfortunately, I have XG1, but I want X. So how do I get X? I just multiply it by X, or multiply by 1 over G1, and now I get the same thing. So if you're ever stumped, that's just the process that I would do. Just lay it out for you, and then it hopefully makes it a more simplistic approach to follow. Okay. And then the last topic, unless there are any questions on that, is Ruth Hurwitz. So the approach, first thing you do is you identify the highest order S row. Then you go S minus 1, all the way down to S to the 0. Now you put your coefficients in, so we'll call this AN, because we'll just associate coefficient AN with the S to the N term. We'll skip over 1. This becomes AN minus 1 or 2. 2, very good. AN minus 4, and on and on and on. Over here, this is AN minus 1, AN minus 3, AN minus 5, etc., etc. To do the next row, now I need to calculate. So this becomes minus 1 divided by A to the N minus 1. And then you got to get the determinant of always the first row. So it's always the first column. It's always the very first column. So it's AN minus 1. And to solve for that next part of your matrix, it's the column just to the right of the number you're calculating. AN minus 2, AN minus 3. So to do the next one, it's still AN minus 1. But now, and I still have my first column, but now it's one column to the right, which is AN minus 4, oops, and AN minus 5. And then once you get all those calculated in that row, you move to the next row, and to the next row, and to the next row. We had a couple of weird cases. So we had case 1. We have a 0 in column 1 only. So 0 in column 1 only means you substitute E for the 0 and continue, right? So you put your little E in there, and then you do your continue all the way until you get to the end of the table. And then you let SE approach 0. And then you check to see if you have any sign changes. Okay. The other case, zeros in entire row. Use the auxiliary equation. How do you find the auxiliary equation? So my A of S is going to be equal to, I have a coefficient here, we'll call it A. And this will put S, and this is where it's going to be hard. So this is going to be the row plus 1. So that's, I'm not sure if that's clear, but you're going to get that value of S. So if this is a row, that's your row number, then you got to go one row higher to get your coefficients. Okay. And then you get B SR plus 1 minus 2. So make sure you get that first coefficient, and then not minus 2 minus 1, sorry. So this is where I get a little bit weird. So this is row 1, and then I'll put first column, and then second column, and on and on and on until you get that. And then you take the derivative of A of S to find your coefficients for your entire row of zeros. And then you replace them. And then you continue. Okay. That gives you your Ruth-Hurwitz. This auxiliary equation is really useful for us too, because auxiliary equation has, let's just say it's an S squared. It has S squared plus B. Well, if I set that equal to 0, what I see is S is equal to plus or minus J B square rooted, right? So this right here is the marginally stable roots. So I can use the auxiliary equation, and we will when we do Routh-Hurwitz, to actually solve for the points on the j omega axis. Okay, those are the only two tweak cases that you need to do. Most of the time, the reason why we look for a row of zeros is, again, we just want to know where the j omega axis is. Or that also could be the bounding for a stable system. So if you have to specify a value of k or a gain that, you know, has a range of k's that result in a stable system, you've got to make sure it stays in the left-hand half plane. So if you find the marginally stable points, then you know it can't exceed that point. So if you remember when you did the homework, sometimes look at a value of k, and you had to do it in two spots. It had to be greater than a number, sometimes 0, but then less than an upper number. And the reason why I had to say less than the upper number is because it started to result in a marginally stable system, and you had to make sure it stayed less than that. And that's what's summarized here. So Routh-Hurwitz, you can just go ahead and solve again for the number of sign changes in that first column. That tells you how many poles are in the right-hand half plane. If there are no sign changes, then there are no poles in the right-hand half plane. Okay. So 5 little questions to focus on. Given the characteristic equation, determine the number of poles in the right-hand half plane. That's generally a good idea to do Routh-Hurwitz. Given a characteristic equation with adjustable parameters, so some adjustable gain, specify a range that parameters of the system remain stable. So that also is on the Routh-Hurwitz. Yes, sir.
Is it going to be asked that it was done by Routh-Hurwitz?
I don't remember. But you can always do that, right? I mean,
Yeah, I know.
like the second one, you have to do it by Routh-Hurwitz. You can't do it with your calculator. I mean, you could just trial and error, but you'd be there for a year to do it, right?
First one.
The first one, it depends if the problem is written or not. Given a characteristic to determine the number of poles in the right-hand half plane. I mean, it's up to you. You can use your calculator or you can just do Routh-Hurwitz. It's totally up to you. Unless I say do the Routh-Hurwitz approach. So if I get a block diagram, so you might need to specify some parameters. Could be first order system, it could be a second order system. And you're given a block diagram, so you might have to do some block diagram math to get the system in the form so you can do the characteristic equation. And then simplify a complicated block diagram. So that's definitely going to be some block diagram math. And then the last one is, if I give you a transfer function, find the parameters. Parameters would be, or could be, I should say, not will be, because I don't want to commit to that, but could be rise time, settling time, peak time, damping ratio, undamped frequency, damped frequency. I think that that's all we'd have. And that's it for the test. Exam stuff that I had. Do you have questions?
Hey, Paul, can you hear me?
Yeah, I can hear you.
Are we going to get any formulas given, or should we write those down on our sheet?
I'll give you a block diagram table, but the rest of the stuff you have to write yourself. Just like on the first test where I gave you the Laplace tables.
Yep.
So you won't need that here, right? Because we're not going to be going back to the time domain. So I would give you the block diagram stuff, but otherwise than that, you'd have to write your own formulas.
All right, thank you.
Yep. Everybody feeling good about this? Good. Everybody's feeling good, feeling confident.
Yeah, 110, yeah.
I don't remember.
Nice.
The last period, like, you've done the.
Yeah, we didn't do that last semester, but this semester I was like, he's like, what should we do for lab? I'm like, you know, and he just and I discussed, it's like, how about doing a review session? He said, that sounds like a good idea. And he sounds like you guys get silly at times. And I don't know exactly what happens. I don't pay attention because
It's good. My brain feels melted afterwards.
in a good way or a bad way?
spend 3 hours on just doing problems.
Okay,
Just mostly just suggested problems.
oh, good, okay. My only concern about the study session is the way that he did the Ruth Hurwitz stuff. I guess some people said in lab it was way more complicated than he presented it. And I'm not saying it's the bad way, it sounded like it was fairly complicated. So hopefully,
We like to take a deep dive,
okay,
look behind why.
it's fine. Yeah, I don't have the reasons behind, I mean, I did a little bit of the derivations, but at some point you just need to know what the approach is, and especially in this class, because a lot of this class in 324, it's not always related to the real world. So I try as much as I can, but recall the whole purpose of these two classes, well, it's two purposes. One is to get a better foundational understanding of the material. You know, more circuits, right? We did a ton of circuits, and so hopefully you have better understanding of the fundamentals of electric circuits, but also it's to help you pass the FE. So that's one that's important to the people who hire you. So that's why this class continues to operate. And then we also have the FE review class, because if we didn't have this class, it would make the FE review class very difficult, because I don't know if anybody's taken that class with Caitlin yet, but there's a lot of math and a lot of stuff that's reliant on understanding how to do Laplace and controls and that type of stuff. Has anybody taken that class? You have? I think it's EET325. Yeah, it's mostly seniors that would have taken it. Now it's required, I think it's required as part of the curriculum just this past year, but the idea is to hopefully give everybody a leg up on passing the FE, which is, as we mentioned in this class, is the first step to getting licensed as a professional engineer, which translates into like an additional $1 to $2 million in your career. So is that important to you? Maybe. It's made a huge difference for me. And I took my PE, I had no guidance. So when I graduated, there was no encouragement. I took the FE and I passed it, you know, I just kind of took it on a whim, if you will. And then once I started, I was like, well, I might as well just get the PE. And so when I was living in Washington, DC, I worked for a company. They never gave me any time off. I had to take a day off because the PE exam is actually during the week, or it used to be during the week. So I took time off, I bought the materials, and I passed. But as soon as I passed, oh, you're a PE now? Well, we got to update your business cards. I was like, well, wait a minute, that's different. Why didn't you tell me this before? I had to pay all for this stuff myself, and all of a sudden you didn't. It's a big deal to you. You never encouraged me at the time. And they said that they realized that was a mistake, and they were going to start encouraging people because it does look good on the business card. So the PE, we're getting a little off topic. All the PE is like, I have some basic ability and intelligence. Because somebody says I'm an engineer. Okay, what are your qualifications? I graduated from college. Well, what type of college? You don't know. But a PE, those are all state boards, and there's pretty much the same exam everybody takes across the country. And the pass-fail rates, if you look on them, let me see if I can actually check pass-fail rates. Anybody ever look? I'll do the PE electrical pass-fail rates. I'll just do P pass rates. Okay. So I don't know if this is a good thing or a bad thing, but about 1 in 3 pass the PE.
Oh, the FE's just about the same.
I don't know. I can look and see. So if you figure the P, let's just say it's 1 in 3, and then let's say. So this is 3 out of 4 who pass it. So let's say 100 people graduate. So 75 people pass the FE, and of that 75, 25 will be able to pass the PE. So when all is said and done, about a quarter of electrical engineering graduates will just do EET and ECO on the same. So about 25% end up becoming PEs. That's why you get a higher salary.
75%.
This is the
75%.
this is the average pass rate of 75%. So if you think about that, that's why, again, it's supply and demand. If I only have 25 out of 100 candidates who have the PE, and I need that for one reason or another, like depending on the work you do, Like if you go work at the shipyard, they don't care. You don't need to be a PE, but if you do any work for non-government entities or even some government entities, like if you were going to design a bridge or the electrical system for Orono, you'd have to stamp that with a PE. The federal government, I don't quite understand how that all works, but for their own ships and equipment, I guess it's maybe for the general public. So if you're working on military, maybe they don't care about military. I'm kidding. But the rules are very different for if you're only going to be servicing military folks as opposed to the general public. So that's the reason why. What's that? Well, like I said, I didn't write the rules, so I don't know. And it's also the PE only applies to the state. So if you want to stamp a drawing, you have to have a PE in that state. That's the minimum you would need. Whereas at the federal government, right, they don't operate under the auspices of any individual state. They have their own laws. So maybe there's different rules about that. I don't know.
So if you're working for like a big consultant, assuming so like you put your offices in Maine, but you're designing something that's out of Idaho, you have to find something.
Well, more than that. So if you want to do the right thing, then we should bring Jude in here as the PE member of the PE board who actually agrees with this stuff. You should not just find somebody to stamp it. You should be working under the direction of that Idaho PE. Because just because that person stamps it, they're saying this has met all standards and the work has been overseen by me. So they just stamp it without actually looking at the material or working on it. Well, I don't know, but it feels really shaky. So for me, you know, when I stamp a drawing or stamp something, I'm always taking it very seriously. Like this needs to be overseen by me. I'm not just going to stamp it because somebody said, hey, can you stamp this drawing? Because then you're personally liable. You screw up, they can come take your house, your cars. Normally, if you work at a company, right, and you make a mistake, aren't not personally liable. But if you PE stamp it, they can come after you individually. So, getting a PE is not just here's an extra $1 million and there's no consequences. Here's $1 million extra dollars and make sure you do good work. So it comes with that additional responsibility.
If you get a PE in every state,
So where can or where can't? NCES has a list. I think there's like 10 or 12 that if you're here, right here, access the report. Oh, I have to get a copy of this, so. I think it's like 10 or 12. All the states in New England except Rhode Island, you can get a PE.
that's just because it's the quality, unfortunately, probably.
Well, it's a little bit, it's a number of reasons. How do you make sure salaries stay high? You limit the supply. So PE boards, they're listening to constituency about, hey, what are the rules that need to be? And some of the constituency are the college programs saying, well, this is what you should do, this is what you should do, this is what you should do. So there's some pressure from some of these organizations to do that. But if you have technology programs that you're right, may not be necessarily the quality, but if somebody is saying that the project has met the demands and they've proven that they can take this test and pass it, why do you even need a degree? So it's just adding another level of difficulty. Like if you were a doctor and you're making $400,000 a year, what if a nurse had been working for 20 years and had been doing the same things that the doctor had been doing and was as skilled or not more skilled than a doctor that just graduated? Why can't they do the same procedures that a doctor can do? Well, you make it so that only these certain doctors can do these things, and that keeps the salaries inflated. Okay. So a lot of it is politics and money things, but some of it is for protection of people. So like, everybody hear what happened last night, the bridge in Baltimore? Yeah, so, you would want that captain or whoever's driving the boat to make sure they know how to drive a boat. So you want to make sure that they have the backup. And that's the problem, which is if you have a junior person who may not have the experience or may not have the ethics to do a quality job. Maybe they just will stamp anything because they want to get paid. Then you can put the public at risk. So that's where, you know, you gotta balance the supply part with it, which is also, we have responsibility to hold to keep the people safe. And mistakes happen. You know, nobody knows what happened in the bridge, but you know, stuff like that happens. No morbid stuff, right? All right, questions? Okay, if there are no questions, I will end class and I will see you tomorrow. Make sure if you're gonna take the exam online, you let me know by like, let's say 10 o'clock tomorrow morning, because I gotta get it all set up. But if not, I'll just plan on seeing you guys in lab tomorrow. Have a great day.